Today we'll continue with the topic on coastal water level fluctuation. Next, we're going to look at shapes or basin oscillations, which is defined as standing waves with relatively long period that can happen in lakes, canals, or bays. Seiche can also happen in open sea coast, but that is known as a meteor tsunami, which we are not going to cover in the present lecture. Here we see how when wind acts on a enclosed water body like a lake, it causes the mass of water to rise on one end, but as a result of gravity action, the mass of water will try to restore to its initial condition, and so as a result of that, an oscillatory motion is produced. If we look at the standing wave, here we can see a standing wave whereby there is node where there's no vertical displacement, and there is also antinode whereby the vertical displacement is the largest. If you focus on this red window, you will notice that the behavior inside this red window is basically the basin oscillations that we have seen earlier, whereby in one end we have the water level rises and falling periodically, opposite to the other end all the time. So essentially, Seiche is a result of the periodic causative force and the restoring force operating alternately, producing the kind of oscillation that we have just observed. Of course, as the Seiche happens over time, after the causative force is no longer present, then its amplitude would eventually decay due to friction, and eventually the water body is able to restore to its initial condition. So Seiche can happen in enclosed water body like the lake, or partially enclosed water body like a bay, where energy can enter uh, and then get reflected inside, whereas they can only partially escape. Or it can also even happen in canals or large rivers, where any energy that enters into it get reflected around, so that is where it can produce the kind of oscillation that we discussed. Now, other than wind stress, shapes can also be induced by wave, by atmospheric pressure changes, by seismic activity like earthquake, or current generated eddies. Here on this GIF, we are looking at a Seiche happening in a swimming pool due to earthquake. You can see how the water is rising alternately on either end of the swimming pool, and it is splashing over to the side of the pool. When Seiche happens, the natural frequency of the oscillations will very much depend on the domain geometry, which basically means the geometry of the water body. Meanwhile, the amplitude of oscillations will depend on the magnitude of the disturbance itself. In some cases, forced oscillation may also occur. That means the frequency of the oscillations is different from the natural frequency of the domain. This usually happens if there are intermittent energy input into the system. Now, if the frequency of the excitation or disturbance is different from the natural frequency of the domain of the basin, then we are likely to get the amplitude of oscillation which are relatively lower compared to the case if the excitation frequency is the same as the natural frequency of the system, whereby that means it is going to cause resonance, and if resonance occur, then that means the siege is going to happen at a very large amplitude. Now we have mentioned about the Seiche amplitude previously. But one thing to take note is that the large-scale horizontal motion due to Seiche is also another major problem, especially when it comes to the harbor or the coastal area, whereby it can potentially cause damage to the mooring line, fender system, and even cause collision between vessels. It can affect the loading and unloading operation, and also if there is a semi-enclosed harbor, then the current coming in and going out from the harbor due to the periodic Seiche oscillation is also another major issue to harbor vessel navigation. Here we can see a picture of the sudden rise of water level due to Seiche. In this case, we have this lighthouse as a reference point, whereby you notice that within less than 10 minutes apart, the entire harbor is flooded with water due to the Seiche. If we define the size of domain using gamma, whether for a closed water body or an open water body, and also that the water depth is defined as d, then we can look at the different mode of how Seiche happens. For the fundamental mode of first harmonic, when k is equal to 0, we will have this profile here in a closed water body, whereby the water level rise and fall at both ends of the basin, like what we observed previously in the animation, whereas the fundamental mode in an open water body will look something like this, whereby again the water rise and fall at one end, but then because the other dam is open, then the node is actually located at the other end. Here in the closed water body, the node is located at the middle, whereas anti-node is located on both ends. For the second mode, or second harmonic, when k is equals to 1, then the Seiche profile looks like this. We have the antinodes on both ends again, and the two nodes inside the basin. Whereas for open water body, again antinode at one end, the closed end of the harbor. We have the node at the open end again, but one additional node in the basin. And next we have the third mode or third harmonic. When k is equals to 2, you can see how the patterns changes. In the form of equation, the period of a particular mode, t, is given by this expression for open basin and this expression for closed basin, whereby, as mentioned, gamma is the basin length, d is the water depth, so we have square root of gd here, which basically is the wave celerity, the celerity of the Seiche, and then we have term 2k plus 1 here and the term k plus 1 here, k being the mode of the oscillations. Of course, for natural basin, the water depth may not be the same for the entire domain. So if we want to derive the Seiche period for natural basin, then we might break down the basin into multiple segments, each segment with a length of gamma I, and each segment with a water depth of di. And so if we sum up the term gamma O square root of gd for each of the segment, then we will be able to approximate the period of the basin oscillations for that particular natural basin. This equation is for closed basin, and this equation is for open basin. Using the small amplitude wave theory, we are able to derive the equation for the particle motion. Here, the first one below the nodal point, the maximum particle velocity can be given by this expression, or they can also be modified in terms of other variable. The average particle velocity is given by the maximum particle velocity times 2 over pi, or basically this expression as derived from here. And one of the important aspects that we mentioned just now is the horizontal displacement. The horizontal particle displacement x can be given by u average multiplied by half of the oscillation period. And so again, if we substitute from the expression above, these are the different expressions that we can write for the value of x. Let's now look at one example. The section of a closed basin has a depth of 8 meters and a horizontal length of 1000 meters. When resonance occurs in this section at the fundamental period, the height of the standing wave is 0.2 meter. Determine the resonance period, the maximum water particle velocity, and the horizontal particle excursion, which means displacement, that occurs under the nodal point. So here we have a closed basin. We are going to look at the fundamental mode Seiche motion. So the equation as we obtained from our earlier slide should be like this. For fundamental mode, k should be equals to 0. So gamma is 1000 meter, water depth is 8 meter. We found out that the oscillation period, which is also the resonance period here, is 3.77 minutes. For the maximum particle velocity, we use the equation from the preceding slides, and we found out that it is approximately 0.11 meter per second. Next, for the horizontal displacement, we use the equation again from the previous slide, and we found out that it is about 8 meter. So imagine in this closed basin, if we have a jetty and there is a boat moored at the jetty, so when the Seiche happen, the boat is going to be pulled out by as far as 8 meter, and then it's going to be pushed in by as far as 8 meter and slam against the jetty and fender system. Obviously that is very, very damaging, even though the Seiche amplitude is not very, very large. For a basin which is partially open to the sea, the resonance that happens can be described or explained using what we call the Helmholtz resonance. Here we see a Helmholtz resonator in the picture. It is used to produce acoustic sound. The physics principles behind it is that when we blow across the opening here, we actually create a region of low pressure near the neck, and it causes the volume of the air inside to be compressed and decompressed alternately, coming in and out of the bottle, so that the sound is then produced with the sound wave speed of v. So the frequency of the sound produced depends very much on the geometry. It depends on A, the area of the opening. It depends on V, the volume of the resonator, and it depends on L, the length of the neck. So the same physics actually happens in partially enclosed coastal bay during basin siege. In basin siege, as we described previously, the basin water level rise and fall, whereas the water mass oscillates in and out of the harbor inlet, which is analogous or similar to the spring mass system used to describe the Helmholtz resonance in a Helmholtz resonator. But specifically for partially enclosed basin in coastal area, the resonance period can be given by this expression, whereby it depends on AB, which is the basin surface area, AC, which is the channel cross-section area, the neck, and then LC, which is the channel length, and LC prime, whereby LC prime is defined as the additional mass outside of the channel length, and is given by this expression, whereby it depends on the channel width W, the channel depth D, and it depends on T, which is the resonance period here. So which means that these two equations are basically interrelated, and so they can only be solved by trial and error. We'll look at this example during our online discussion.